Okay, gang, we're going to do 3.1. I'm just going to start off with some formulas and some explanations of the formulas. Okay, so the first thing I want to talk about is if we have a graph, and I'm going to call this function f, okay? And I'm going to put 2 points on this function. So the first point has an input of x. So this coordinate here is going to be x, f of x. That would be the coordinate, the xy value. Then I'm going to move over a distance of h, which would make my next input value x plus h, right? Because I started at x, I moved over a distance of h, I added h, so this new input value is x plus h. So this point then is, the input value is x plus h, and in function notation this would be f of x plus h, and that would be the xy value. So if you recall from algebra, intermediate algebra, if you want to calculate the slope in algebra, you would have done m equals, do you remember the formula? y2 minus y1 over x2 minus x1, and that would have given you the slope. Now let's do the same concept, but instead of writing it in this notation, let's write it in function notation, which is a fancier notation, okay? So y2 in function notation would be this point. This is your xy. Right, so y2 is this value here, minus y1. Can you figure out who y1 would be? In function notation, that would be f of x. Alright, minus your second x value, who would that be? Right, that's this guy. This was our second x value. Minus x1, which be your first x value, which in this case would be x. Alright, now I'm going to simplify this, which means x minus x will, these like terms will combine. So this will come out to be f of x plus h minus f of x over h. Does anybody remember who this is, what we call this? This is a very special definition. Anybody remember? We call this the difference quotient. The difference quotient. It's basically finding the slope in function notation. Alright, so if you find the slope between 2 points, you're basically finding the slope of this line. You're finding the slope of this line, okay? Now, if you go through 2 points, do you guys remember what that's called, what kind of line that is if you go through 2 points? That's called the slope of the secant line. So another thing that we could call this is the slope of the secant line. Let me just spell that a little clearer. Secant. S-E-C-A-N-T. Secant line. Slope of the secant line. If you draw a line through 2 points, that's the slope of the secant line. Now, I want you to think of a particular concept that I'm going to describe. So as I look at these 2 points, I want you to think about shrinking h, letting the distance of h go to 0. So if you shrink the distance of h, the next point might be like here, right? I'm shrinking this h value. I'm bringing it back. I'm shrinking it like this way. I'm bringing it over to the left. So now the secant line looks like this. Okay, so now the secant line is this line. Now keep shrinking h. So now maybe I have it here. Right, so now the secant line is going through these two values. Right, so I'm altering the secant line. So first I had it here, I'm shrinking h, so now it's here. I'm shrinking h, so now it's here. What happens when I shrink h all the way back to here, then all the way back to here, then when I do that, how many times, oops, let me get that line better. Okay, technically I can't see it really well because I got so much drawn there. If I like zoom in on it, it looks a bit like this. Okay, so as I pull h all the way back, what happens is h goes to 0. I'm only touching the graph at one point. Do you guys know what that means when you touch it at one point? That's the slope of the tangent line. Okay, so secant's where you're touching it twice. Tangent's where you're touching it once. So as you let h go to 0 of the difference quotient, that's what we call the slope of the tangent line. You're only touching it at one point. That is an extremely powerful concept. I almost, like, it's almost hard to say that in words or to express it enough in words. Like, the jump in understanding or skill set at this moment is extraordinary, because up to this point you've really only been talking in averages, like, oh, on average I drove to work at 35 miles per hour. You know, you can all, mathematically we've only been talking in averages up to this point. Once you hit this moment when you understand the slope of the secant line, you're doing what we would call instantaneous rates. You can tell me how fast you're driving at this second, at this second, at this second, at this second, right? It's not like, oh, the average of the whole thing, right? This is a way more powerful concept. I can tell you how fast a cloud is moving at this second, how fast a rocket is moving at this second, how fast a supply is selling at this second, how good the demand is at this second, how fast a wound is healing at this moment, right? It's a way more, how fast somebody's heart rate, blood flow, I mean, it applies to so many things. Instantaneous feedback is way more powerful and informational than average of any. Average can be construed, where instantaneous is way more powerful. So this is what we call the derivative. The slope of the tangent line is what we call the derivative. It is enormous jump in understanding and concepts. It's like, yeah, you're reaching such a monumental event right now. I don't even, short of having a parade for you at the moment, I hope I'm expressing how impressive it is that you've come to this moment, and you understand mathematically how to do an instantaneous rate. Okay, so that's what we're going to focus on in this next chapter, chapter 3, of doing the mechanics. How do we mathematically calculate a derivative? And then in chapter 4, we'll look at how do we apply it. But we're now going to work on, like, the algebra of how to do a derivative. Like, how do I mathematically calculate it? And then later on we'll use it. Okay, so if you, this right here, this is read as f prime. You don't usually, you can say derivative. I have to watch what I say here. There's lots of ways to reference this, just like you might have like a lot of different nicknames, you know, yeah, you could just be referenced by a lot of different names, you know, depending on who I'm talking to. I'm Professor Wieland, or I'm Rachel. My sister has a nickname for me. Like, there's lots of different names that reference me. And same thing with derivatives. We could call it f prime. We could call it the derivative. We could call it the instantaneous rate of change. You've got to know that we're talking all about the same thing there. Okay, the other thing I want to point out is that there's different ways to write the derivative. These are all different notations to write the derivative, okay? So for right now, in the beginning, you're going to see me just use this and this one and this one. You will see me use this one where I have to, but I'm going to stick with this and this because I think it's just easier for you to learn it first. I don't too often use these. I will, but it would be very rare. Okay, and then this is read as the derivative of y with respect to x. We're taking the derivative of y with respect to x. Oh, and let me also be clear, because this right now, what we're doing, this is the formal definition of the derivative. And later on, I'll show you like quick little tricks and quick ways to find the answer. But right now, we're going to do it the formal way, which is a bit longer, just to add to your understanding and sort of really flesh out your toolbox on how to do this stuff. Okay, so I'm going to get rid of the G in these when I do these. So I want you guys to find the derivative of this function using the limit process. Now the limit process is what I just derived for you guys. Oh, you know what? I'm already at 11 minutes here, so let me end this video. And when I come back, I will do that. Okay, so catch you. Bye-bye.